Testing.
All right, good. We're going to pick up our lecture from where we left off last day, and we were talking about static features in a class that normally does not have any static features. So I mentioned that you can have static fields. Remember, a static field, there's only one copy of the field. It's owned by the class. It's not owned by the individual objects in the class or that are constructed from the class. And so our Domino class had a field called int. It was public, static, and final. A field of type int called min value that was public, static, and final. So remember, public means that any class that can see the Domino class can use min value. Static means there's only one copy of min value, and it belongs to the Domino class. Final means that you can only assign a value to min value once. So when I write min value equals 0, that's the only time I can do this in a program. So if you have a public, static, final, primitive field, the class is basically trying to say there's this primitive value that's a constant that you might find useful if you're using this class. So if you try to change the value of min value, so it doesn't matter where you do this. You can do this in a main method inside the Domino class. You can do this somewhere else. If you try to set min value, the compiler will complain. It will say that you can't change min value. It's final and it's already been assigned to. So a final field means that a final public static field in a class basically means the thing is constant. If you have an immutable reference type, so not a primitive type, but if you have an immutable reference type, so something like a string, that's also final, I guess, and public and static. The class is again trying to tell you there's this string that's a constant value. So remember, strings are immutable, meaning you can't change the characters of a string once you make the string. So this string peekaboo is forever peekaboo, right? It's always the letters P-E-E-K -A -boo, right? There's no methods in the string class that let you change the letters of the string. The field X is marked public, static, and final. So final means I can only assign a value to X once. If I try to reassign X to something else, so nothing to hide.x, ICU, doesn't compile. The compiler says you've got a final field, you can't reassign to it. All right, so what about arrays and lists? So arrays and lists are not, they are not immutable, right? If you have an array, you can change the elements in the array. If you have a list, you can remove things from the list, you can add things to the list, and so on and so on and so forth. So if you try to play this same trick, so I make a public static final list, it's called empty. So it looks like somebody's trying to make an empty list, and it's always supposed to be empty. They make it static and final because they think, oh, this is a constant, right? The problem is this is not logically constant. The field empty always refers to the list that was made here. But you can make a main method, and you can use the list and call a method using the list. So I can add something to the list. So I can add oops to my empty list. And now my list that was empty is no longer empty. Right? That works. The compiler is perfectly happy with that piece of code. And so what was once, or what is supposed to be an empty list, is no longer empty. And now your field has probably an inappropriate name. Right? And so if you have a mutable reference type, right, you probably can't make it final and have it be a constant. Right. So if you want a constant inside your class for some reason, you can't make it a mutable reference type because somebody has, if you make it public, somebody gets a reference to that field, they can change the state of that field. Right. So mutable types are not logically constant. It doesn't make sense to make them public, static, and final most of the time. Okay, so what about static methods? Static fields are relatively uncommon. When you're making a class, typically you make static, non-static fields. Static methods are a little bit more common though. So static methods are per class members of a class. All that means is that the methods belong to the class right? When you want to use the method, you use the name of the class to call the method. You don't need to make an object, right? So just like static fields are often called class variables, a static method is often called a class method, right? It belongs to the class. So in our Domino class, we can add a static method if we wanted to. So here we have a method called isValueOK. It simply checks if value is between 0 and 6, right? Because on a domino, the maximum values of your sides are between 0 and 6. So it's pretty easy to implement, right? You just test if value is greater than or equal to min value and less than or equal to max value, and away you go. So notice that a static method can use a static field belonging to the class, right? Min value and max value are both static in Domino. A static method in Domino can use those static fields, right? Because the fields also belong to the class. So the method has access to the static fields. What you have to remember is that in a static method, there is no this object. Right? You don't need an object to call isValueOK. Therefore, the value this is not defined for a static method, right? Because this refers to the object that was used to call the method. Right? So if you have some object, so you have some class that has some non-static method, and you use the reference to call the method. That, right? But inside some method, obj is this. Right? So we have a static method. So in a static method, we have a class name. We don't have an object to call. You don't use an object to call the method. Therefore, there's no this inside of a static method. Right? And so what that means is that you probably, if there are no parameters, or if there are no parameters whose type is the same as the class, right? You can't access the fields, the non-static fields used inside the static method. Right. So in other words, if you try to write value is greater than or equal to this dot side 1, that doesn't work, right? There is no this, right? Or this dot side 2, again, there is no this, so that doesn't work. The exception to this rule is if you pass in a domino object here. So if you pass in a domino object here, called D, then you can write D dot side 1 and D dot side 2 inside the method. Right? So if you're not given an object, you can't access the fields of you can't access the non-static fields of the domino class. If you are given a domino object, you can access this non-static fields of that domino object. Right here, we're not given an object, so we can only use min value and max value inside the class. Right, those are the only fields that are usable inside this class. Sorry, inside this method. All right, so when you call a static method, right, you use the name of the class to call the method, just like when you access a field, a static field, you use the name of the class to access the static field. However, just like when you access a static field, you are allowed to make an object and then access the static method. This is legal, but considered bad form. Right? So if you're trying to access a static method, use the name of the class. Don't use the name of an object, even though it's legal. The reason you don't use you don't write it this way is because a more experienced programmer will look at this code and say, isValueOK is a non-static method, right? You need an object to call it. Okay, so earlier in the course, so in assignment 1, I don't remember what assignment 2 was, but in assignment 1, you made a class and everything inside the class was static. So that's an example of what's called a utility class. Okay, so remember what a class is. Excuse me. So remember in Java, a class lets you define a type. But really, more generally, a class is basically a model of a concept or a thing, right? So a string is a model of a sequence of characters, right? A list is a model of a sequence of items. In Java, a class is usually used as a blueprint to make new objects, right? So most classes in Java are used to create objects. However, sometimes, so more rarely, it is useful to create a class called the utility class that is not used to make objects. Right? So these classes, you're not making any objects, so there are no constructors in the class. right? Or at least there's no constructors that someone can use in the class. And in these classes, everything is static. So there are some examples of static classes in the standard library, but there's not many. There's only a relatively small handful. So for example, math is an example of a utility class that's part of the standard language. Right? The math class contains a bunch of methods that are basically mathematical functions. The arrays class has a bunch of static methods that operate on arrays. The collections class has a bunch of static methods that operate on things like lists. And so the reason for having utility classes is that they group together a bunch of related in fields and methods where you can use those fields and methods without making an object. Right, so math groups together a bunch of mathematical constants and functions. Right? You don't need a math object to compute the cosine of a number. Collections groups together methods that operate on Java collections like lists. Right? You need to make a list to call the method, but you don't need to make a collections object to call the methods in collections. So a utility class is never used to create objects. If you can make an object using the utility class, so if the math class could make a math object, then it wouldn't be a utility class, right? It would be a regular class. So when you use a utility class, only the class itself occupies any memory because you're not making any objects with the class anyway. Right, so here we got math.cos and math.sine. Right, notice there's no math object flowing anywhere. Right, there's no new math anywhere in this code. Right, so we never actually need to make a math object. In memory, all that exists is the class itself. Right, so the math class, when you use the math class, it gets loaded into memory. Right, it has some static fields, so pi and e, representing the mathematical values pi and e. Right, you can call sine and cosine. Right? But there's no math object that gets created to make sine and cosine. To compute sine and cosine, sorry. Okay, so how do you make the utility class? So it turns out it's very easy. You have to remember two things. So I want to make a utility class that lets you calculate equals mc squared. So this is Einstein's mass energy equivalence equation. If you've never seen it before, it doesn't matter. It's just an equation. Right, so that's the only reason I'm using this as an example. Okay, so there's two things you need to remember. Everything is static. That's easy to remember. There's one other thing that you have to remember, and I'll show you that in about 5 minutes. Okay, so how do you make a utility class? Well, it's just a class. So public class, give it a name. Right here, I'm calling it relativity. You can call it whatever you want. Right? So the math class is called math. Collections class is called collections, right? Methods that operate on arrays, not surprisingly, it's in a class called arrays. Okay, everything is static, right? So I want a field here that represents the speed of light in this case. So the speed of light happens to be relevant if you're calculating for this particular equation. Anybody using this class might want access to the speed of light. So let's make a constant that gives people access to the speed of light. Right, so we make it public, static, and final. Physicists call the speed of light c. They normally use lowercase c. This is Java. It's a constant, so we make it an uppercase c. Right, and its value is roughly 3 times 10 to the 8. Right, so 299792458. The Einstein's equation is E equals mc squared. Right, so m is the mass of the object. So we have a method. It's also static, right? Everything in a utility class is static. So to calculate the amount of energy equivalent to an amount of mass, right? You just pass it the mass, multiply it by c squared, and that's the amount of energy. And you're almost done. There's your utility class, right? It's a class. Everything is static, right? Nothing else changes. If you want to use the class, remember it's a utility class. So to call the methods or to use C, you use the name of the class, right? So somewhere else in another class called 1 gram, right? We define an amount of mass, right? So the mass is in kilograms. So this is 0.001, so that's 1 gram, right? So basically a few grains of salt would be equal to 1 gram. Right? If you calculate the amount of energy equal to 1 gram, you get this number down here, right? So roughly 9 times 10 to the 13 joules, right? Which is a very big number. Right, that's very large. So if you could actually convert 1 gram of mass into energy, you produce a lot of energy. And that's how your nuclear reactors work, right? They convert a small amount of mass into energy and thus powering several thousands of homes, which is nice. Right? Okay, so there's something funny about the class that we've created so far, right? We've made a utility class, we've made everything static, but there's one problem. So you have to remember what Java does if you make a class and you don't put a constructor in the class. Right? It makes one for you. Right. So in our class, we do not have a public constructor, right? But you can write that and everything is just fine. And so in other words, you have a utility class, but you can now make an object, right? Which you're not supposed to be able to do, right? That's not the purpose of utility class. If you try this with the math class, so if you try to write java.lang.math m equals new math, it won't work. Right? The compiler will tell you there's no public constructor. Right? So remember, if you don't define any constructors, the Java compiler generates one for you. Right? It generates the no argument constructor. Right? No arguments here. And so what that means in this particular case is you get that constructor, even though we didn't create it ourselves. Right? So we don't want this to happen inside a utility class, right? We never want to be able to write that. So what's the solution? Make a constructor and make it private. That's the solution, right? If it's private, it's only usable inside the class itself. So anybody who's using the class outside of the class can't call the constructor. Okay. So private fields, constructors, or methods can only be used inside the class that it's declared in. So if I go and put in a private constructor, it doesn't matter what constructor. Here I'm putting in the no argument constructor. You can put in whatever one you want, right? It does nothing. The only purpose of this constructor is to stop people from making objects, which is weird because normally you need a constructor to make objects, right? But here we're making it private, so anybody outside the class can't use this constructor, right? Now, if someone tries to write that, the compiler complains and says there is no publicly accessible constructor, right? And so now we've got a complete utility class, right? If we have a class, everything is static except for the constructor. Constructors are never static, right? The constructor is private. That prevents other people from making relativity objects in this case. Right? And there's an example of a complete utility class, right? They're generally very easy to implement. Everything's static. There's generally only a small number of fields, and all of your methods, if they need a field, they use one or more of the static fields, right? And your methods basically look like Python functions now. Okay, so when you the two things you need to remember: everything is static. You should have a private, empty, no argument constructor, and that stops people from making objects of your class type. And that's all there is to say about utility classes. They are somewhat uncommon in Java. Right? Normally, when you make a class, the purpose of the class is to make objects. Okay, so there's a class where everything is static. It is not uncommon to have a class where most of the features are not static, but you still have some static methods. And one of the common reasons why you might have a class with static methods is to create what's called a factory method. So these things are called factory methods because they make objects. So a static factory method, it's static. That's why the name static is in the name, right? So it's a static method that returns an instance of the class, right? So in other words, it makes a new object of the same type that it is it makes a new object of the same type of the class that it's defined in, right? It's factory method because it makes a new object and returns a reference to the new object. That's sort of what a constructor does, right? So remember, a constructor, you write something new constructor, right? The combination of the new and the constructor makes a new object that the caller can now use, right? So a static factory method, internally, it makes a new object and returns a reference to the object that the caller can now use, right? So static factory methods are sort of like constructors, right? They create and return a reference to a new object, right? The big difference here is that unlike a constructor, your method has a name and you get to pick the name, right? Remember, constructors, you don't get to pick their name. It's always the name of the class. That causes a problem in some cases. Okay, so remember our point class, right? So we have a two-dimensional point, right? You can make a point. There's a constructor that has an x and where the caller passes in an x and a y value for the point, right? So the caller passes in two double values. If you've taken calculus, you've probably heard of the polar form of a point, right? So the polar form of a point, you can define the location of a point by saying how far the point is from the origin, right? So that's the radius, right? And what is the angle relative to the x-axis, right? So here is our angle theta, right? You can compute the location of the point. So the x and y coordinate of this point is r times cos theta and r times sine theta, right? If you haven't taken calculus yet, don't worry about it. This is not important, right? The actual details are not important. What is important is that you can make a point by passing in an x and a y coordinate, but someone might want to make a point by passing in a radius and an angle. So if you decide that you want this feature in your class, you might say, well, look, I want a constructor that takes in a radius and an angle. Right? So what is the type of the radius? Well, these are real points. So the distance is probably a real number. So you'd probably use double. Right? The angle is probably a real number. So you'd probably use double here too. Right? And notice now you have a problem. It's easy to implement. Right? Implementing the constructor is dead easy. X equals r times math cos theta, y equals r times math sine theta. Right? But the problem is you have two constructors and their types in their parameter lists are both double and double. So now you have two constructors with the same signature. Right? Remember, the signature of a constructor is the name of the constructor plus the list of parameter types. Right? So here they're both point double double. And you're not allowed to have two constructors with the same signature in the same class. So now you're stuck, right? You can offer one or the other, but you can't offer both. And so what's the solution here? Turn one into a static method, right? So you solve the problem by replacing the second constructor with a static factory method. So static factory method is static. Internally, it's going to make a new object and return a reference to the object. This is not a common name, but in Java, this is called the named constructor idiom, because a static factory method looks like a constructor, but it has a different name. So that's where the named constructor comes from. An idiom is just a way to do things in a particular context. Okay, so the static factory method here is easy to implement. It's static. Right? It returns a reference to a new point. Right? So it returns a reference to a new point. I get to give it whatever name I want. So here the name polar makes sense because this is the polar form of the point. Right? And now I have the parameters here. So r, the radius, and theta, the angle from the x-axis. Right? There is no method called polar in my class. So I don't have to worry if there's another. I don't have to worry about duplicated method signatures in this case. Right? Implementing the method is easy. Right? You calculate the coordinates of the point. So r times cos theta, r times sine theta. Right? Now it's a factory method. It has to return a new point. So you just make a new point and return the point. So return new point 2 x, y, and away you go. Right? And that solves our problem of being able to create a point by passing in two double values that are not the x and y coordinates of the point. Right? So we have our original constructor, right? And instead of having a constructor that makes a point given its polar form, we provide a static factory method instead. Right? And so this is very common this sort of use of a static method is very common in the Java language, right? Many static methods are factory methods, right? They create a new object and return a reference to the object. So in that point 2 class, if you actually ever look at the implementation of it, you'll see there are a bunch of other static factory methods. Right? There's a method add, subtract, multiply, divide, and negate. Right? There's also a non-static add, subtract, multiply, divide, and negate in all these classes, right? And so the reason that there are two, or a static and non-static version of each method, is the following. Sorry, I just have to pull up the class. Wrong. Point two. Okay, so let's go find one of these static methods somewhere. Okay, there's add. There is subtract. There's multiply. Sorry, I didn't put them all together and I should have. Okay, so there's a version of add up here. All right. There's a version of add right here. So the way you call this add method is you write p dot add and then some vector v. That, right? Non-static. So you have an object, you call the method, you pass in some parameter. Right. So that method there, mathematically, it computes something like p equals p plus v. Right. So it takes your point p, it adds the vector to the point, and it changes the coordinates of the point. Right. So in other words, this changes p. Changes coordinates of p. The static version does not change the coordinates of p, but it still adds the two things together. All right, so the static version would use like the following. So remember, the static version returns a new point object, so you probably want to remember what the object is. Point two is static, so we use the name of the class. We call the method add p and v. Right, so the static version of the method computes p plus v, right? But it returns a new point, q. So this is like you wanted to do something like that instead, right? So I don't want to change the coordinates of p, so it does not change. Right, so the first version changes the object that was used to call the method. Right, the second version does not change the object, the point two object that was passed into the method. Right, and that lets people that lets users of the class pick which method is most appropriate for the problem they're trying to solve. Oh, actually, it's on the next slide. So here you go. So the non-static version of add changes the point used to call the method. Right, so the non-static version computes something like p equals p plus v. Right, the static version does not change the coordinates of p, but it still adds p and v together to give you a new point. Right, so that's like you wanted to make a new point q that's equal to the point p added to the vector v. So if you start looking in the Java libraries, in the classes that we've used, you'll find all sorts of static methods. Well, not all sorts. You'll find some static methods, sorry. So in the integer class, you'll find a method called value of. Right? Value of takes in an int and returns the corresponding big I integer. Right? So remember, integer is the wrapper class for int. Right? Whenever you use an int, whenever you're using an int, you can often convert it to a big I integer automatically. Right? What happens is the language converts the integer I for you. It converts the int I into an integer by calling the value of method belonging to integer. So in other words, the language silently calls value of for you when it needs to convert an int into an integer. Right. The string class has all sorts of static methods in it if you go looking inside the class. Right, so there's a method called format that returns something called there's a method called format that lets you format a bunch of different arguments and return a string using the formatted arguments. The arrays class is full of static methods because it is a utility class, right? So it has a method called copy of that lets you copy an array, which is handy. You don't have to write the loop yourself. And you can, again, if you poke around in the Java standard library and look at the classes that we've used, you'll see that there are many, not many again, you'll see that there are some static methods. Most of them are factory methods. All right, so that's all I have to say about static features in a class. Any questions so far or about today's lecture? All right, so we're moving on now to the next lecture. And so this is, there's going to be probably 2 lectures on this. So there's this method called equals in the Java language that turns out to be very important. Right. So remember, we saw this method called toString, right? The toString method returns the string representation of an object, right? We replaced the definition of toString in the classes that we've created so far. So in point2 and in counter, probably somewhere else, right? So we replaced the definition of toString in those classes. And you can see that after replacing the methods, replacing toString, you can now print out objects of your type. Right, so when you print out a point, you get round brackets, coordinates of the point. And so the toString method came from this class called big O object. Equals also comes from this class big O object. Right? So suppose you create a class. Right? Every time you make a class, you end up extending big O object. Right? So whether you say so or not. Suppose you create a class knowing what you know right now. So you make your point2 class, for example. Right. Inside point2, in the lectures, we have not replaced the definition of equals yet. Right. However, you can still call equals using a point2 object. Right. So for example, I can make the point P. Right. It's the point 1, 2. Right. And I can write something like P equals P, which hopefully is true. Right. P should be equal to P. It's the same object after all. Right? And this works just fine, right? The reason it works, even though we haven't defined equals in our class, is because point2 got the equals method from big O object. Okay, if you write P2 equals P, like that, you can now write, sorry, P2 gets the value of P, right? Or P2 is assigned the value of P, right? You can write P2 equals P here, and you also get true. Similarly, you can write P equals P2, and you will also get true. Okay, what happens when we make a new point? I make a new point, 1, 2, right? It has the same coordinates as the original point, right? If you write P3 dot equals P, you now get false, right? And so, right, P equals P is true, P2 equals P is true, but P3 equals P is false, right? So what's going on here? Okay, so if you draw the memory diagram of what's happening here, right? So P is a new point. P2 is not a new point, right? There's no call to new, right? There's no call to a static factory method here, which would call new, right? So P2 equals P simply means that P2 refers to the same object as P. P3, there is a call to new, so there is a new point object. So here we've got, that's P, or P refers to this object here. Right? When you write P2 equals P, right, P2, its value is equal to this value here. Right? So P2 gets the value 600, which means it also points at this object here. Right? P3 is a new point, so a new point gets created. New point gets created. Right? Its coordinates are 1 and 2, which are the same as the other point. Right? But this is a distinct object from this object here. Right? So when you use equals, or when you use equals from big O object, right, it tests if 2 references refer to the same object. So in other words, it's exactly as if you had used equals equals to compare the 2 values. Right? So x equals y is true if and only if x and y refer to the same object. Right? So here, P and P2, they both refer to that object here, right? Their value is the address 600. Right? So P is equal to P2. P and P3, well, they refer to different objects. Right? P refers to that object here. P3 refers to this object here. Right? The number 600A is not equal to the number 700A. So the object version of equals returns false in this case. Right? P and P3 do not refer to the same object. For a class like point2, that's probably not what you want. Right? For point2, if you have 2 points with the same coordinates, you probably want them to be equal, right? So most value type classes should support what's called logical equality. Object equals supports what's called equality of identity, right? 2 objects are equal if and only if they are the same object. Logical equality means 2 objects are equal if and only if they have the same state, right? So for points, 2 points are equal if and only if they have the same coordinates. And it turns out that implementing this method was considered surprisingly hard. So in the early days of the language, if you were to open up a textbook, you would pick 3 textbooks and look at how they implement equals. There was a pretty good chance that they would all have a different version of equals, which is strange because equals is kind of fundamental to the language, right? So Angelica Langer, she's a a programming consultant. If you follow this link here, it'll take you. You can find this quote in her webpage. Right. And so she says that one would expect that overriding equals should be easy, right? And the reality is far from that. There is an amazing amount of disagreement in the Java community regarding the correct implementation of equals. This is no longer true, right? But back in the early days when people were first starting to use the Java language, there was a lot of confusion on how to actually implement equals. Okay, so there's in today's world, there's basically 2 common forms of equals, right? And there is a third, quite uncommon version of equals that I'm not going to explain how it works, right? But I will tell you how the other 2 work. And so there's going to be 2 different ways. So what I'm going to talk about right now doesn't always do exactly what you want it to do, right? The other method, so if what you want to do so the second method does something slightly different, and that second method might be the one that you want, might be what you want equals to do, right? But it's a little bit funny because what you want equals to do changes depending on the context in which you're using it in. Okay. So our requirements for equals in this course for today is that an instance should always be equal to itself, right? X equals X should always be true, right? So an object is always equal to itself. If you compare an object to null, you should always get false, right? And you should never throw an exception, right? So X equals null is always false. For today, or for now, for the time being, only objects that have the exact same type can be equal, right? So only a 0.2 object can be equal to another 0.2 object, right? So for example, a 0.2 object can't be equal to a string, even if the string happens to be the same string that toString returns. And finally, this is the thing we're really interested in, right? We really want 2 objects to be equal if they have the same state. So 2.2 objects are equal if they have the same coordinates. Okay, so requirement number 1, an object is equal to itself, simply means X equals X is always true. Right? X equals Y is true if X and Y are refer to the same object. Right? Equals equals, when you apply it to 2 references, tests are the 2 things the same object. Right? And so you can easily implement requirement 1 in your equals method. Right? So inside the 0.2 class, we're going to now override or replace the definition of equals. Right? Equals always has this signature here. So it's always public. It always returns true or false. Its name is always equals. This is the confusing part for most new programmers. Right? The type that you pass in, its parameter, is of type big O object. Right? For 0.2, it's not 0.2. Right? If you put in public Boolean equals 0.2 p, right, you're not replacing the definition of equals. You're adding a new version of equals, right? You're adding an overloaded version of equals. That's not what you want to do here. You want to replace the version of equals that we got from big O object. So the version of equals that we got from big O object, its parameter is of type big O object. Right? Now remember what this means inside of a method, right? So I'm going to change this here to equal. Obj dot equal something else. I guess we'll call it another. Okay, so remember, when you call the equals method with an object, inside equals, this is obj. Oh, sorry, I can't do it that way. Sorry. O dot equals, right? So when you call equals with a reference O, inside the method, this is O, right? The parameter that you pass in on my lecture slide is obj. Oh, I probably shouldn't call it other here either. Sorry. Oh, and now it's called P, I guess, or something else. Right. So when someone uses the method like that, inside your method, that object is this, and that object is obj. So keep that in mind as we continue on. Okay, so I want to know, so equals is supposed to return true if that object and that, sorry, if this reference and this reference both refer to the same object. Right, so inside equals, I want to test, is this and obj, do they refer to the same object? So the way you do that is by testing, is this equals to obj? Right. So if that's true, then this and obj both refer to the same object. So we can immediately return true in this case, right? Because basically what someone has done is they've written something like x equals x, which is always true. Okay, is that clear to everybody who's here? Yes. Yeah, okay, good. So technically this doesn't have to be here, right? So if you leave this out and you implement the rest of the method correctly, that's fine, right? But it is cheap to check, and it stops the rest of the method from running, which may not be so inexpensive to test for. Which might be more expensive to run, sorry. Right, so technically this doesn't have to be here, but the condition is cheap to check, so you might as well do it. All right, for today's, so I guess always, one of the requirements of the equals method is that if you write x equals null, the answer is always false, right? And an exception is never thrown, right? So inside of our method, remember, x will be this. The null will be, obj will be equal to null, right? And you can check if obj is equal to null very easily, right? So if obj is null, right? So equals is again the operator you use if you want to test for if something is null, right? We know the answer must be false, right? So we're going to return false immediately here. In this version of equals, this if statement has to be here, right? And it has to be done at this point in the method. You can't put it somewhere else, right? Because the next step relies on obj not being null, right? So you have to do this either here or up here, right? So it has to occur now. All right, the next step is 3. So we're only going to let objects that have the same type be equal, right? And so remember here that inside of our method, that the way the method is defined, sorry, is that the object that's coming in has the type big O object. So we somehow have to ask obj, right, what is your actual type? So what happens in Java is that if your parameter is of type big O object, you can pass in any reference type here. Right, so you can pass in a string, you can pass in a list, you can pass in a .2 object, right? These will all work. And the reason this works in Java is because of something we haven't talked about yet. And so object is what's called the superclass of all classes in Java. What that means is that every reference type can be substituted for you can substitute any reference type for big O object. Right, so if I have a list, I'm allowed to pass it to this method. If I have a string, I'm allowed to pass it to this method. If I have a big I integer, I can pass it to this method. Everything's fine. Right? So when you pass it to the method, as far as equals is concerned, it's gotten a big O object, right? But the actual type, right? It's still part of this big O. It's still part of OBJ. And so we now need to ask OBJ, what is your actual type? Right. So if we pass in a string, I want to know, is OBJ actually a string? Right. If we're forcing only objects of the same type can be equal, I want to know inside equals, is OBJ a point2 object? Right. So the way you ask an object for its type is with the method called getClass. Right. So inside the big O object class, there's also a method called getClass. Right. And what that means is, given any reference variable, you can call getClass using that variable. Right. GetClass returns something funny. It returns a big C class object. Right. That big C class object tells you something about the type of the object. Right. So for point 2, getClass is going to return a class object that says this object is of type point 2. So I can write, I want to know, are the two object, or sorry, is this, right, and OBJ, do they have the exact same type? So I can ask this for its type by using getClass, right? I can ask OBJ for its type by using getClass. If they're different, then the two objects have different types, and I know they can't be equals. So if the class of this type of this object is different from the class of this object, we can immediately return false. Right? And that gives you requirement number 3. Finally, we're at requirement number 4. And I'm probably going to have to stop here. So in requirement number 4, we're now going to test, do the two objects have the same state? Right? So if you get past this if statement in point 2, right, what do you know? Right? Well, you know OBJ and this are different objects. Right? You know that OBJ is not null. You know that this and OBJ have the same type. So in other words, you know that both objects are point 2 objects. So here, there's going to be some code that now goes in and compares the X and Y coordinates of the two objects. And so we'll look at how to do that on Monday, I guess. Right. So remember, next week you have a test. There is an announcement on OnQ that does explain what's covered on the test. Basically, what you need to know for the test is you need to be able to implement a class. Right? It has some constructors, it has some fields, it has some methods. Right? It's only 50 minutes, so at most, so the classes that you are asked to implement are not very large. Right? You don't need to know about equals. You don't need to know about what did we do last time? The previous class. You don't need to know about static stuff in the class, right? It's all, everything in on the test is non-static methods, non-static fields. Okay. So that's all I have for you for today. Have a good weekend, everybody. I'll see you next week.